Okay, so today I'm going to talk a little bit about regression and correlation. And the main thing with regression and correlation is we do that to be able to find the relationships between different measurements that we make. And that's, I mean, you're definitely going to, if you haven't done it already a lot, you'll definitely do that a lot, that you do different measurements and see what's the relationship between these measurements, and then build a model and think about what these relationships mean. What I'm going to go through today is first looking at regression. So this is to estimate what the relationship is between variables. And most of the time we're going to work with linear regression, and that's always preferable if we can use a linear model, but that's of course not always the case. And we're going to then see when we need to, what the assumptions are for the linear model, and also when we need to go to nonlinear regression. And the other part of the lecture is on correlation. And correlation is to, we calculate correlation coefficients to quantify how strong the association is between the different variables. And this is, of course, very important, because if we just see a weak correlation, then of course that could, and we only have measured a few points, that could of course just be because at random we got a spurious correlation. And then we'll also look at that correlation is not always a great way to measure this, how strong the association is, because it's very dependent on how many measurements you make, and also on what the distribution of the data is. So if we start looking at now relationships between two variables. So we have one variable that we plot on the x-axis and one on the y-axis. And so to the right we see that there is really no relationship between the x and the y. So we just, there is some variation in y, but pretty much over the whole range of x we don't see any specific pattern. So in this case we would just say that there is no relationship. But to the left we see that quite a strong linear relationship between x and y. And so the first step always when we have done measurement is to make a plot and look at the data, just to see if it looks like we expected, if there are some strange things going on. So here now, so that was either we have a relationship or not. We can also on the left side we had the same as last slide, we have a linear relationship, and to the right we have a non-linear relationship. And as I said before, it's much easier to deal with linear relationships than it is with non-linear. But you'll definitely come across non-linear relationships also often. So then a relationship can be weak or strong. So to the left we see that the measurements align very nicely, roughly along a straight line, and there is not much deviation from this line. While on the right side we see a much weaker relationship, and one that there's still some relationship there, but it's definitely the error in our measurements is quite large, so we won't be able to very clearly define what's the relationship. So now if we look back at these, so we had the strong, weak, linear relationship, and the nonlinear. So now if we try to fit a line through these, so this is what's called linear regression. So we try to find the line that best represents these points. So you can see that if we have the linear strong relationship, we can draw a line that very well represents the data. But when the relationship is weak, we have larger deviations from the line. And if in the case of nonlinear, we try to force it, the line on the nonlinear set, but it doesn't succeed very well. So a good thing to do in this case is not just plot the data, but after we've found a line that we think is good, we can plot how far the different points are from the line. So we plot the residuals. So again, what we see here is that in the case of the strong relationship, we have just very small deviations, and they look more or less random. There's no specific trend as we go along the x-axis. Then we have the weak linear association. Then we see that we have much larger deviations, but still there is no specific pattern to this. They look more or less randomly distributed along the y-axis. But then if we have quite a strong nonlinear relationship, that as in this case, and we try to fit the line, then we see that the residuals there is a shape to it, that there are first larger positive deviations, then in the middle there are negative deviations, and then again positive deviations, as we see here, because we've sort of forced the line onto a relationship that's not actually linear. So these are two very good plots to make always. So first you just look at the data as it is, the relation between two variables. Then you try to fit a line, and then you look at the residuals to see if the linear model seems to be okay. So now, if we look at this, how to fit the line actually a little bit more formally, we see that we have our independent variable x, and then so this is x of I. So we have the different measurements. In the plots before, we had 20 measurements, so that I would have gone from 1 to 20. So those are the measurements of one variable. And then associated with each xi is a dependent variable, the yi. So again, we in this case have for each yi, for each xi, we have one yi. And then the linear model is that we have an intercept, that's beta 0, and a slope, so beta 1 times x. And then we have, so this is the linear part, and then we have an error, that's whatever is left over. So these are the deviations from the line. So now if we then look at what the assumptions are, so the main assumption when we do linear regression is that the relationship between the variables actually is linear, and this is and this is important to know, because something that could happen is that we measure in a small range, and then it looks linear in that range. But then if we extrapolate outside of the range, we don't really know if the linearity is valid outside of the range. So we might, so that extrapolation is always dangerous then. So the other assumptions are with respect to the errors. So we we assume that errors are independent for each measurement, that they are normally distributed, and that their mean is 0, and there is a constant variance along the measurements for different values. And we'll see later that the constant variance is not often, when we do measurements, not true. So we'll have to deal with that in a different way. And one way is to use the variance to weight the values. So if we look at the linear assumption, so in this case, it looks, if we plot the data and then show our regression line and then plot the residuals, one way, as I mentioned, is to check the linearity assumption is that we don't see any structure in the measurements, in the residuals, and that's pretty much true here. That it looks quite random. So if you're interested in seeing how so that if we contrast that to the case when the data has a nonlinear relationship, but we still fit the line, we see then that we have this structure in the residuals that is indicative that the linear assumption was not correct. So the other one is that in this case we have a constant variance, and the way that we can detect whether we have the easiest probably is to see in the residuals that the variation, the deviation from 0 is roughly constant, while in this case we have a variable, the variance increases with x. So we see that here we have smaller variance than for larger values of x. So again, this is important to make sure which of these cases we have. So now if we go back to the linear regression model, so again we have two measurements. So we have measurements of x and y, and then we're going to try to find a line that describes the relationship. So, and then a line would be an intercept plus the slope of the curve times the x variable. And then we have the random error. So in the case, if we then try to estimate the line, so now we have removed the error because here this is the estimated intercept and the estimated slope, and from the x then we can calculate the estimated value of y. So this will represent our actual line. And then so given these, we now have a few measurements of 1 through n, or pairs of x and y, and then we want to find the slope and the intercept given these measurements. And one way of finding the best line is to minimize the sum of the squares of the residuals. So what it is that if we sum thus the squares of the errors, which are the residuals, we get an expression and we need to minimize this. So who remembers how we find the minimum? Anyone? If we have a mathematical expression and we want to find the minimum, what do we do? Sorry? Yes. Yeah. So we have two parameters here. so we want this sum that the derivative for beta 0 is 0 and the derivative for beta 1 is 0. So this is what we then use to derive how to, and it's actually not a very difficult derivation. It looks quite long and involved, but it's so eventually we'll end up with what's in the yellow box. So we can express beta 1 and beta 0 as a function of either the sums of x, the sums of y, the sums of x squared, and the sums of x times y. So this, if you're interested, you can go through this in detail. But then the nice thing is that in Python and in other languages also, it's very easy. There is a function that you can call to get the slope and the intercept. And that's it's in this SciPy stats package. And it's just called linregress. And you enter two arrays, x and y. And then you get the slope intercept. You also get the correlation coefficients, which we'll talk about later. A p-value, which tells you if what the chance that this would happen if you had randomly distributed values for x and y, and also it will give you the standard error of the slope. So then if we look now at the case that we looked at before, which we have the strong correlation, strong linear correlation between the two variables, if you're interested in seeing how these plots were generated, it's pretty straightforward. So first we set x as, in this case we had 20 points, so between -1 and 1, and then y is equal to x plus a randomly distributed normal distribution. And then we calculate the slope and intercept here, and then the line is actually the slope times x plus the intercept. And then we can just plot these, and then these are the plots that you get. So it's really very easy to use the linear regression here in Python. And then if we look at the weak correlation, the only thing we change in the code is that instead of 0.1 times the normal so we add 0.4 times the normal noise to get the larger deviations. And actually, so I haven't put it on the website yet, but I can put the code for all the plots that are in the PowerPoint if you're interested in looking at how. So it's very similar to this and quite straightforward to generate these. So now, so far we've looked at quite well-behaved cases, but let's say that we have an outlier. So in this case, we have our data looks nice and linear with just small errors, but there is one outlier that has a very big deviation. So if we now do a linear regression on this data, we see that the line is not going to be very good. So this is the disadvantage with the least squares method, is that it is very sensitive to outliers. So that's something definitely to remember, because often when you do measurements, you have outliers for different reasons. So but there are more robust regression methods, but the most commonly used linear regression is very sensitive. So what you see in the residuals here is that you're going to have a trend, and that's, you see here that there are negative deviations here below the line, and then this part is above the line. So again, this is not the right method to apply to that. And the reason why it's so sensitive is because you take the square of the deviation. So large deviations will contribute very much disproportionately. So now if we look at go back to nonlinear data. So in this case, again, if we do a linear regression, but the underlying data is not linear, we see that it doesn't succeed very well. So there are a few solutions to that. One is that often we can transform nonlinear data to linear data. And actually, so the data that's shown here is exponential. So here we could, for example, take the log of the y values, and then end up with with linear data. And that's in a lot of cases we have that can do that kind of transformation. There are other transformations that could be useful, as long as you sort of know your data, and especially if you have a good model for what the data should look like, then you can do this transformation and go back to the linear. And the other alternative is to do a non-linear regression. So of course what we did was to fit a intercept times the slope times x, which is a linear model, but we could also fit any arbitrary function. It will be much more difficult to derive a closed mathematical form, but that doesn't matter. I mean, we can easily solve these numerically. But the problem is that if we do nonlinear regression, it's often much more difficult to know when how to weigh the different values and what is the shape of the curve. So that it's not. I mean, people have done linear regression for a very long time and have really figured out how to do that well. But for nonlinear regression, it's not so well worked out. So it's always preferable if you can do the transformation back to a linear model. Okay, so far, any questions so far? So who has done linear regression? 3? Okay, so that's, yeah. So I think 3 people put up their hands, yeah. That's not very, I mean, soon you will, more of you will do it, I think. So then, correlation. So now, so far we've tried to find the best line to sort of to explain to show the relationship between two variables, but then the correlation coefficient will tell us how strong the correlation is, so as you see here this is the regular Pearson correlation. So this assumes again linearity, so it has it's very closely related to linear regression. So it has the same assumptions also, that with regards to the errors, and also that the data should be linear. So let's have a look at what what we do here is that this is the average value for y, and so we take the each measurement and subtract the average, and then for the x we do the same. We take the x value and subtract the average of all the x's. And then we divide by the squares of those sums. So if you, into this, if we would have a linear relationship between the y and x, so you can see, so linear relationship would mean that the y minus the average of y is equal to a constant times x minus the average of x. So if you would put that into this expression, it would come out that the correlation coefficient is 1. So for any linear relationship between the two variables, we would have a correlation coefficient of 1. And that would be the, yeah.
Sorry, I was just going to ask a question about, I was just going to ask about linear, assuming, how do you determine if you're going to have a linear relationship or not? I know you gave those slides before, you were saying as the error needs to be normally distributed, you need to have similar variance, the mean needs to be around 0. Are those the general criteria, or are you looking at, are you making a subjective decision looking at the spread of data if you have a, what appears to be a nonlinear relationship? Because as the relationship gets weaker, it might be tougher to make that.
Yeah. So I mean,
when do you decide to intervene and transform? When do you decide not to? What's the? Yeah.
So I mean, a lot of cases we actually have too few data points to really say, and in that, if you don't, if you can't clearly see a trend or have a model that you believe in, then it's probably better not to transform, because I mean then you probably introduce more error. So if you don't have any evidence to transform, it's better to stay on the safe side. But yeah, it's definitely a problem. But you would look at, if you have enough data points, you can make a histogram of the errors and see how close it is to normal. You can do a quantile plot to see if it's normal. There are also other statistical tests that you can apply to test for normality. But most of these things require that you have quite a few data points.
Yeah, well, that's my question, because I know, likely if you have a threshold I was kind of given, it's kind of around that 50. Like you need a number of data points to be able to make these decisions. But in basic science, where we're doing stuff, where people are pulling up correlations on an N of 7.
Yeah, I mean, usually
it's very challenging to kind of make the call between what to do.
Yeah. I mean, usually then people have some model which they are testing, so that I mean but if you just have few data points and you don't have any idea of what the relationship is, that's very difficult, definitely. So now this, of course, is we have a perfect linear relationship, either a positive relationship or a negative relationship. In this case, the correlation coefficient is 1, and in this case it's -1. And those are the two extremes, and we always have that the correlation coefficient between -1 and 1. And these are the best correlations. So if we now add more noise, we see how the correlation coefficient goes down. So even here, we've added a little bit of noise, and we see that the correlation coefficient has decreased, but not by a lot. And the same in the negative case. If we add even more noise, now it's starting to quite noisy, but still the correlation coefficient is reasonably high. Then as we go, it becomes more and more noisy, and finally there is, in this case, no correlation at all. So it's always good to maybe see in your, if you have done some measurements and you have a certain number of data points that you have measured, to do simulations to see if you, for the same case, have a lot of noise, what would this look like? And whether, and to make sure that you're not just measuring noise. So this is from Wikipedia. Just you can have a look. They have different examples of what different correlations look like. So again, we have the positive 1. This is 0.8, 0.4, and then 0, which there is no correlation. The other thing to remember is that if we have nonlinear cases, so these are all cases where there is definitely a relationship between the two variables, but when we calculate the correlation coefficient, it will be 0. So that's so definitely since we're looking for a linear relationship, it won't pick up any patterns like this. So so far we have actually looked at when the variance is constant. But another, it's actually quite, in a lot of measurements that you do, it's not going to be the variance that is constant, but the variance divided by the mean. And so this is the definition, it's called the coefficient of variation. So meaning that the standard deviation is proportional to the measurement, and this is so in a lot of cases this is what we see. So if we then look at now, so these are simulations using a uniform distribution, so meaning, so x is uniformly distributed like on all the plots that we've seen so far, and then we for different coefficients of variation, that's plotted on the x-axis, we look at what's the correlation coefficient. So if we see, for example, if we only have 10 points, it's not a very well-defined relationship between the coefficient of variation and the correlation coefficient. If we go up to 1,000 points, the spread is much smaller, but still there is quite a spread, and even for if we have 100 points, there's definitely a large spread. So, but what we can see here, that if we have a coefficient of variation of 1, meaning that error is of the same order as our measurement, which is a large, so it's 100% error, we get about little bit over 0.4 in correlation coefficient, which is surprisingly large for such a big error. So this is for the uniform distribution. So this is one problem with with using correlation coefficient. Another problem is that for different distributions you get different relationships. So here we saw in the last figure we looked at the uniform distribution. So now we're looking at 100 points. So now if we look at the normal distribution, looks very similar as the uniform distribution. But if we have a log normal distribution, so this is a much we have it's a skewed distribution, so we have quite a lot of outliers. So in this case, we can get very high correlation coefficients, even though there is the error is the coefficient of variation is very large. So, for example, if we go in at if we compare with the normal distribution, if we look at CVs of 100%, so most of the values here are under correlation coefficient. Most of the time we get less than 0.5. But in the case of the log normal distribution with the long tail, we get most of the time larger than 0.6. And so that's so to rely on the correlation coefficient as sort of a measure of the quality, which is often done, is not, one should be very careful with that. So now, again, so we look at a few different cases, that what happens with the correlation coefficient. So here we have our nice linear relationship, and we get the correlation coefficient of 0.98. But if we have just one outlier here, it goes down to 0.63. And this is, except for the outlier, it's exactly the same data points here. So we have, so again, the same as when we did the linear regression. One outlier will cause a big drop. It will make a big difference. Then we have the nonlinear case. Again, we can revisit that. So in this case, if we use the regular Pearson correlation coefficient, we get 0.74, which is not a great correlation coefficient. But the solution to this is, of course, like before, we can transform the data, or we can use a correlation coefficient that doesn't assume linearity, which in this case, the most commonly used is the Spearman rank correlation. So instead of correlating the actual values, we just rank them and correlate the ranks. And then, so in this case, if we use the rank correlation, we get a correlation coefficient of 0.93, which is what we would expect, because it looks like the data is definitely, there's a clear relationship here, but it's just that it's not linear. So then when we do a correlation, of course, one thing that we want to ask is there really a correlation, or is this just random? So we can do a hypothesis test, and there's actually very well-defined relationship between the correlation coefficient and the p-value, but it depends on how many points we have. So here, for 10 points, we have the correlation coefficient on the x-axis, and then the p-value log scale on the y-axis. So we see that, for example, if we have a correlation coefficient of 0.5, in this case, it ends up being a p-value of 0.1. For example, so that would so we would have to go to quite high correlation coefficient before it becomes a significant correlation. Now, if we go to 100 points, then a correlation of 0.5 would be approximately a p-value of 10 to the minus 7, which is highly significant. And if we go to even higher points, the p-value for the same correlation coefficient becomes smaller and smaller. So this is something to think about, is that if we want to measure if we want to really check that whether there is a significant correlation between two variables, it's better to measure more points than less. So now just a few slides about how this can be then applied to analytical measurements. And so ideally, when you do measurements, this is, I mean, a lot of times it's not done like this, but ideally one should generate a calibration curve like this. So you should preferably know what you're measuring and how much, and be able to add different amounts. And so here, what people have done, so this is quantifying a peptide. So they have synthesized a heavy isotope variant of this peptide and added to the background that they want to measure the real peptide in. So this is now in a tumor digest. So what we've added is this is isotopically heavy peptide, so we can distinguish that. So there shouldn't be any endogenous heavy peptide in there. So we can add different amounts, and then we want to see that our measurement response is linear. So now observe that these are both log scales, just because we want to show that we can do a linear measurement over a few orders of magnitude. But typically what happens with this is that at some point, if you go down in concentration, you won't be able to measure it. So these gray points are below the limit of quantitation, and you can't, there is no longer any relationship between how much material we added and what we're measuring. So we definitely want to establish this limit so that we can do later on, when we do our measurements, we know that if we measure something below here, all we can say is below the detection limit, and we can't really say anything more than that. So when doing analytical, there are a few sort of definitions that people have come up with that are very good to think about. One is the accuracy. So the accuracy is how well you can measure and how close what you measure is to what really is in the sample. And this is to distinguish from precision, which is precision is how you can repeatedly measure the same thing and what your reproducibility, how reproducibly you can measure. So this little figure here shows so if we have a reference value or what's actually in the sample, so accuracy is the distance of your sort of mean measurement from this reference value, and the precision is the width of the distribution of what you measure. So then robustness is something we talk about when we look at, for example, how the measurements change when we store them for a long time, if we measure in the summer or in the winter, I mean, different humidities, and those all go into the robustness. And of course, to do these, establish the robustness is very time consuming, because you have to probably spend months or a year to establish that measurement. So a lot of people don't. But in clinical chemistry, they definitely establish these and are very careful to get the right get these things right. So then something that we're very interested in is the lower limit of detection. And so this is the lowest amount that we can distinguish from background. Limit of quantitation, which is usually slightly higher than the limit of detection, and is where we have a linear range also. And then linearity, so we have the lower limit of detection. We also usually have an upper limit of detection. At that point, we can get saturation. So we need to establish this linear range that we can do the measurements. So, and this is what's shown here, that up here we can get this saturation, and down here we go below the limit of quantitation, and we can no longer measure. So we really need to stay between these two limits in this range where it's linear. So then again, just precision and accuracy. So this measurement here, we get good precision and good accuracy, while in this case we have slightly worse precision, but a lot worse accuracy. So then, to summarize, so we talked a lot about regression, and we can always fit a straight line through data, and we've talked about how to distinguish whether that's a good idea to do or not. But the other thing we should think about is how we use this regression. And this is just an example of a bad use of the regression. But definitely that's something you should very carefully think about how you actually do use it. Then we talked about correlation and all sorts of things. We can find all sorts of correlations that might or might not make sense. So this is a correlation between chocolate consumption and the number of Nobel Prize laureates. So the thing is that if we find a correlation, we should also make sure that it does make sense. Because especially if you try measure a lot of different things, like let's say you do RNA-seq and you measure the expression of many genes in many different samples, and you try to see if you find for each pair of genes if they're correlated. You're going to find a lot of correlations, but the question is, do they make sense or not? So that's all I had for today. Next time we'll talk about experimental design. Thank you.